And let's just go ahead and start. Tom, I couldn't give you a proper introduction off the top of my head, so I'm going to let you just introduce yourself and just jump right in.
Sure. So I'm Tom Fiddaman. I'm with Ventana Systems, where I've actually been for a long time now. But I got my start in system dynamics at Dartmouth College with Dennis Meadows and Barry Richmond. And actually, the reason I'm here is that the system dynamics courses met on, were the only thing in the engineering school that met on Tuesdays and Thursdays, so I could go skiing Monday, Wednesday, Friday at the Dartmouth Skiway. So serendipity. But anyway, I kind of wear two hats. One is as a consultant on a variety of projects. I try to focus most on energy and climate work, like the early versions of C-roads and N-roads. But I also do quite a bit of work in the health space and in kind of a crossover between health and environment. Lately, I've been working on chronic wasting disease in deer, which is a very interesting and sad problem. Today, I'm going to talk about our experiences in state COVID policy in the early days of the pandemic, and then the details of some of the methods that we used in that modeling project. So automated calibration, maximum likelihood, Kalman filtering, Bayesian inference methods, and Markov Chain Monte Carlo being kind of the primary pieces. That's a ton to bite off in one chunk. So I will run through this kind of quickly, but as kind of a companion to this, I recently recorded a series of workshop videos for the SD conference that cover the same topics as a how-to, and they include sample models of all these things. And in the references at the end, I have a link to these. And incidentally, I will share these slides. I'll post them on my blog, which is metasd.com, and also send the link to Wayne so he can share it with everybody. So you don't need to take detailed notes. Again, I said I'm going to go kind of fast just because there's a lot to cover in the time, but do feel free to jump in with questions along the way. I probably won't be able to watch the chat, but if somebody wants to monitor that and interject with anything that's particularly timely, that'd be great. Otherwise, hopefully I can leave some kind of questions at the end.
I'll monitor the chat, make sure that if I can speak aloud for someone who doesn't have a mic or whatever, I'll do that.
Great. Okay, I was just rereading System Dynamics the Next 50 Years, and in general, I like it, but I disagree with Jay Forrester's perspective on data in that reflection. So he says things like fitting curves past data can be misleading. If you have enough parameters, you can make the model do anything you want in a sort of a meaningless sense. And that getting the model to fit the data doesn't really reassure you that the model actually contains the structure that's causing behavior in the real system, and so on. And I think, in a sense, these critiques are partly well-founded because they come from a time in which people were doing lots of sort of linear regression or stepwise regression or econometric models with lots of parameters and vacuous structure. and so forth. And so these were all appropriate critiques. But these critiques don't have to apply to us now when we have ways of calibrating good dynamic models. So my vision of how things work is as follows. So this is kind of the classic system dynamics path. You work with a group to generate some reference nodes in a dynamic hypothesis and identify the question to be answered. You then start building model structure using a mix of kind of face validity tests with the subject matter experts and reality checks, extreme conditions, conservation laws, balancing your units, things like that. And you end up with a vetted structure that you can use to do policy experiments, to get insights about the decision to be made. So that's kind of the classic cycle. And then you can get fancy and do the same thing under uncertainty by adding some a priori uncertainties about some of the key parameters or testing variance on the structure and improve your decisions by essentially testing policies under a variety of cases, not just a single best guess case. If you add data, what you're really doing is adding a new set of tests that you can perform on the model by comparing the model to the data. And in so doing, you learn about the model. So there may be some model structures that are inconsistent with the data, which you can then reject, or you can refine the structure so that the model can replicate the data. But you are equally likely to learn about the data in the sense that the data doesn't mean what people think it means, or the data is simply wrong. And you can also, even if you don't have real data, you can even create data by synthesizing it from essentially a copy of your model with noise and other limitations added to the measurement processes. So it brings a new set of tests, but I think the key is that these are necessary tests to perform, but they're not sufficient. So this was the problem Jay was alluding to, that if you're only looking at the model data fit, you're leaving out the subject matter expertise and the reality checks and the a priori uncertainties. And therefore, you might be doing things that fit the data, but are otherwise fundamentally stupid in some way. Once you have the data, there are lots of model data comparisons you can make. You can use automation to, or algorithms to get a lot more mileage out of the data that you have. So you can use optimization to automate the fitting, although doing it by hand is often pretty effective. You can use it also to extract confidence bounds from measurements that you make with the data. And then that becomes useful input to things like Monte Carlo or sensitivity simulations, because you can translate your uncertainty from measurements into uncertainty in the future or the context in which decisions will be made. And then finally, there's kind of a mindset shift you can make to become a Bayesian system dynamicist. And mechanically, that basically involves supplementing the model data comparisons you're making with priors on what the parameters ought to be, and maybe also some workflow or interpretation changes in how you think about all this. And I'll illustrate that in a little bit more detail. So, and of course, all of this, there should be some outer loops wrapping this, because ideally you want to track your decisions, see how they turn out, and then learn from this whole process, modify your data collection and model construction methods, and maybe refine the questions that you're asking of the model and so forth. This is an awful lot to think about on top of kind of the classical process. But on the other hand, I think you ignore the data at some peril. So the benefit of doing kind of classic SD with a light informal data input is you save a ton of time on data collection and processing. And you can reallocate that time to client interaction and scenario experimentation and quality checks on the model and so forth. So there is an opportunity cost. And the other opportunity cost is cognitive load on the participants in your modeling process. There's a lot for you to think about and a lot for them to think about. But on the other hand, there's a big missed opportunity. You don't learn about the data or from the data, which means you're excluding a set of quality tests that you could otherwise perform on the model. If you are taking the model to the public, you also have less face validity because you can't replicate history. And you probably have much less objective basis for stating how uncertain your results are, stating the confidence bounds on your parameters or on the outcomes from the model. And that becomes particularly acute when you talk about, say, the joint uncertainties within a parameter set as opposed to individual parameter uncertainties. And you certainly see those kinds of things playing out in lots of real world problems. You know, in COVID, it's uncertainty about R0 or generation time or transmission rates. And in climate, it's uncertainty about climate sensitivity and how that is confounded with ocean heat uptake and aerosol forcing. So in a lot of decision-making contexts, these things turn out to be really important. So I'll first tell you a little bit about a state COVID modeling project that we undertook in the early days of the pandemic, kind of April to June 2020. And then I'll back up and talk about some of the methods in a little bit more detail. So we became part of the modeling team in the kind of the governor's emergency task force in a red state with a technically savvy governor. And they had a bunch of questions. The primary one was just tactical interpretation of the data, but then they had some immediate decisions to make, like should they convert a stadium into a field hospital? And how many tests should they order? You know, 1,000, 5,000, 10,000. And then a little bit later, it became what happens if we reopen the economy and cancel a lot of the kind of enforced social distancing measures that were in place initially. And the bottom line is if we hadn't been data focused, there wouldn't have been a project, at least not for us. So the model was kind of an enhanced SEIR model. I think by now probably everybody's seen lots of these in the COVID space. So pretty much the classic SEIR, but with some higher order delays in the infection processes to match the observations of the inter-infection times or generation times. We had a vector of non-pharmaceutical interventions and some explicit behavior hypotheses, at least. And in kind of another layer, we had a detailed hospital sector which elaborated on some of the resources that might be needed. And then we had a lot of data streams for comparison to these. We had kind of the classic cases, hospitalizations, deaths. We also had some information on the composition of tests, who's getting tested. And then we tried to triangulate behavior through things like cell phone mobility. And then we had some kind of drivers or scenario variables, weather, population, density, things like that. And there was a lot of detail. So the model was arrayed into 2 risk groups by 50 states. And immediately that means you have a 50 by 50 interstate matrix, although we reduced that to the adjacency terms so that it's not quite 50 times 50 parameters, essentially. We had 45 different state NPIs, so our restaurants closed, our gyms closed, are people able to do telemedicine, things like that. And these were basically a bunch of driving step functions for which we tried to estimate effects. And then 5 hospital resources, so ventilators and different classes of beds and so forth. So this means the model's pretty big. 7,300 stocks, 13,000 constants. Most of those are sort of fixed a priori. They're, for example, zeros in the interstate transmission matrix. But about 300 of them were in the parameter set that we estimated. And we had 2,300 time series, of which we used about 400 for estimation. There are a lot of things we kind of looked at a few times for verification of particular narrow purposes, but didn't use intensively. So big parameter space, but also big data space in this case. This meant a pretty complicated architecture. So we had data streams coming in from daily updates of COVID tracking, which is the tests and hospitalization. We had Google mobility data and a couple other cell providers. We had some ad hoc surveillance data from the state. And then we had the team at Boston University's non-pharmaceutical intervention step function database and census data and BEA and things like that. And so we had a kind of a mostly automated chain in which a data guru got up in the morning, slurped in all the new data. It passed through CSV files, sometimes through R, into a data model that integrated everything, and then dumped out a CSV file that got checked into a Git repository. And then 2 hours later, when we hit Montana time, the model team, which was myself and David Peterson and Alan Graham, would get up and check out the data from the repository, import it into the model, work on the model, and launch some optimization runs. The optimization runs would then produce output files and Markov Chain Monte Carlo samples of parameter sets, and we check those back into the repository just to preserve the complete paper trail. So I haven't tried this, but I think in principle, we could go back to any day of the early days of the pandemic and recreate the state of the model and the state of the data and rerun the experiments to understand more about how things worked at that time. The challenge was that every time we did this, the cycle tended to get disrupted by a call from the governor's office saying, we've got a press conference this afternoon, we need some slides about X, and X might be something we hadn't even thought about yet. So it was kind of extremely stressful and turbulent to try and do this kind of thoughtful, formal modeling calibration process overlaid by this very ad hoc reactive process. The bottom line may be that we just needed a bigger team, but I think that was true for everybody everywhere at the time. So when we calibrated the model, we did a mix of things. We did some conventional kind of hill climbing optimization in Benson. That's the Powell method. And then we did Markov Chain Monte Carlo, which I'll talk about a little bit later, which gives you not just the best guess or the maximum likelihood estimate or the peak of the distribution, but also lets you explore the full parameter space. So you get a joint distribution of parameters. One thing that took us a while to work out was that we initially assumed that case and hospitalization and death counts were distributed via the Poisson distribution because they're count data. And it turned out that there was more dispersion in those than you would expect from the Poisson distribution. So we had to switch to an over-dispersed Poisson distribution. Interestingly, independently and by a slightly different derivation, Hazir Ramandad's team discovered the same thing. And kind of our early default, which was just use the normal distribution and adjust the variance to match Poisson, actually didn't work. You just got lousy fits. And that's partly because Poisson distribution is skewed and partly because of this over dispersion problem. Because the model was big and we needed to do a calibration every day, we needed a really big computer. So we had a 60-core HP server, and we used a parallel version of Vensim that's actually now available to you if you want to email us. That was the only way we could kind of get enough throughput to get a calibration done every day. So just a few examples. Around April 15th, 2020, the data point circled in green occurred. And actually, people kind of panicked when they saw that data point, because essentially, I think the mental model was that what was going on was the right trajectory. So we simulated, we updated the model to reflect this new data point. So people were panicking that things were growing super exponential or something. And the model calibration, or at least the maximum likelihood, was actually the left panel here, which kind of says, don't panic. And it turned out actually that part of the reason for this kind of upward excursion in the data point was that there was a big expansion in testing underway, but people didn't have a good handle on how much testing was actually going on in the field. So this is the perspective from our control panel in the model, our calibration control panel. 10 days later, basically, the model was correct that the big expansion was largely an expansion in testing, not a big uptick in positivity of tests or in sort of a change in the composition of the population, or a big uptick in prevalence, which was really what people were worried about. So just a couple weeks later, things weren't looking so bad. And in particular, if you look at the top right panel, fraction positive was basically holding steady. So the real issue was just an expansion in testing. When we made, so in order to kind of combat this problem of chasing the data, or chasing the noise in the data, really, we tried to present people with confidence bounds on outputs a lot, so that they would kind of get used to thinking about things probabilistically. The problem is the confidence bounds were pretty big. But interestingly, early on, even though we weren't looking at multiple waves of disease and things like that, the predictions were already pretty reasonable. So this is from May 24th, and the actuals are pretty central to our confidence bounds on the future evolution, in spite of the fact that there's really a lot of kind of structural difference between the model and reality here. Another way we tried to present the uncertainty in the outcome was looking at essentially giving people contingency tables for uncertain outcomes. So this one compares uncertainty about how effective is your isolation with kind of a policy option, which is how much do you reopen the economy, relax all the NPIs. And our point, which I think was largely ignored, was that there are some very nonlinear risks here as you move towards reopening the economy fully. If you don't have other effective policies in place, then the death toll goes up very rapidly from 700 in the blue circle here to 4,000 in the upper red corner. But you could mitigate that by other effective policies. Unfortunately, that didn't really happen, I think. So there were lots of kind of interesting outcomes that happen in fairly rapid succession here. We advised, for example, that they didn't need to convert the sports arena into a field hospital because there'd be some early warning from the model if there was going to be a problem. And probably your limiting resources were not going to be the equipment, but the staff. But they did it anyway. It was never used, and so on. Interestingly, in spite of, I think, a lot of kind of positive contributions of the model to early thinking about the problem, as soon as it became clear that the death toll was relatively modest on kind of a macabre scale, in a sense, the response choices became fully politicized and models were squeezed out of the debate. Our contract was not renewed and we were not replaced by anybody else. And as a result, the health economy trade-offs were made with no explicit model input or explicit reasoning. We had proposed that if the central issue was really the economy versus health, then there should be a model of economy versus health, and these decisions should be made out in the open. And basically, that didn't happen. This was a tough environment. The data were extremely sparse, especially early on. Tons of uncertainty, tons of time pressure. And even after the data stream started to improve, you had long delays in the physics of the problem, long delays in the reporting process. There was an ongoing problem that testing composition was unknown. So there was lots of ad hoc testing of whoever walked into the clinic, almost no surveillance of the general population. So you didn't have anything like a random sample that would give you real insight into prevalence, and so on. So lots of challenges in the data, but in a sense, a lot of the questions were about understanding the data. So now let me shift gears and talk about some of the methods that we used. And this follows kind of a sequence in the sense of get the data, build some model structure, start doing model data comparisons informally, and then gradually formalize things more and more. And the way this worked in this project and the way I like to do it is to essentially have two tracks. So the left track here is kind of the calibration track, where you get more and more formal and more complete in your specification of likelihoods and errors and all that stuff, and you do more and more sophisticated analysis. But the right track is, in a sense, more important. This is the classic decision-focused SD track, where you use the model to start designing policies, test them first deterministically, and then with uncertainty and a lot of sensitivity analysis, and refine the model structure and the questions you're asking as you go. So I think these things need to happen in parallel. And one nice consequence of doing things in parallel is that you're kind of observing Jim Hines' admonition that we should always be done. So you always have an answer coming from the policy track of the modeling, and at the same time you're refining your understanding of the data, what the data says about the model, but you're balancing the two so that you're not diving so deep into the data that you never think about what does all this mean for the decision we're trying to make. So the fundamental process is to view the model as a model of the process that generated the data. And actually, I think that's, again, consistent with Jay's perspective, that we should be modeling not just the data that occurred, but essentially all possible data that could occur. Sort of the idea of modeling not just a company in 2022, but all possible companies in a given business. So that means we have to have the dynamic structure right, kind of that's the classic SD piece. And then for interacting with the data, we need some additional stuff, which is understanding the distribution of errors in the measurement process, the distribution of disturbances to the system state, so random things that are happening that we don't know how to model or simply don't know about. And then if you're kind of going Bayesian, you can also include priors on your unknown parameters, or also on things that are not necessarily parameters, but kind of informally characterized behaviors, essentially your reference nodes. So if you want things to oscillate, you can essentially put a prior on the amount of amplitude or frequency of oscillations that you're seeing. So then you ask, if this model's right, what parameters are most likely to have generated the data and simultaneously to be consistent with our priors? And you can think about this as a frequentist. If I keep creating new histories with this model, keep repeating the experiment, what's the chance that the parameter will be in my confidence interval? Whereas a Bayesian is looking at this more like a subjective belief about the true value of the parameter. One thing you can do, which we did a lot of on a small scale in the early days of our project, was test this not with the real data, but with synthetic data. So you can use the model to generate data. You take essentially the model's true trajectory, interpret that as the truth, the true parameters and so forth, and then add some measurement noise to a few of the series in the model, and maybe downsample them so you have less frequency and a shorter time horizon. And then you can take another copy of the model and see if you can use it to estimate what those parameters were. And that tells you how well your process is working. And it's especially interesting if you have an adversary. So one person on the team creates the synthetic model and another person tries to reverse engineer what was going on in that model with another copy. That's a useful starting point. And actually it may be smart to do that before you even start collecting the real data, because you may discover that some of the data is useless, or some of the data is particularly important and needs some focus because it has a lot of leverage on some state or some outcome in the model. So then, next step, we build a control panel that compares the model and the data series. And actually, I showed you an example of that earlier. This was our control panel in the state model. And we actually have a couple of these for different kinds of data series. So you can just see by eyeball whether the model fits the data, and you can also see how extreme the noise is here. Once you've done that, as soon as you can calibrate by eyeball, you now know the model series and the data series that you want to compare, and you can automate that using the optimizer. So you just create a payoff or an objective function that describes how well the model fits the data, and then you use some algorithm to iterate over a list of parameters to maximize the payoff. And again, there's more detailed examples of how all this works in the workshop videos that I've recorded that are listed in the references here. So actually, this will get you a long way, because you'll find out whether the model can even generate the behavior modes that are seen in the data. But it doesn't tell you things like, what are the confidence bounds on my parameter choices? For that, we need a little bit more information, which is, in a sense, we need to formalize our description of the likelihood that the model generated the data. So what do we mean by likelihood? So a likelihood is just a probability density function. The one I'm showing here is from the normal distribution, but you can quickly look up others on, Wikipedia or Wolfram Math World or any stat site. And actually, Benson builds in a number of these. So the likelihood is just a function that describes the probability of getting a given observation, given the truth, and the scale of the errors, or the distribution of the errors around the truth that you expect. So for the normal distribution, the likelihood is 1 over root 2 pi sigma e to the minus model minus data over sigma squared divided by a pesky factor of 2. So we're comparing the model to the data. This says that the bigger the gap between the model and the data gets, the smaller the likelihood gets. So the farther you get from the truth, the lower the likelihood of observing a given value is. The errors are squared, which is why people do ordinary least squares estimation. And sigma here characterizes the scale of the errors that we expect. So if sigma is large, then we sort of tolerate large deviations between the model and the data. This becomes much more convenient if you take logs. So as the log likelihoods convert multiplication into addition and essentially separate all of these terms. So what does this look like? It just says that as you start to move away from the truth, the likelihood of observing a given value declines parabolically. But you don't have to restrict yourself to a parabolic assumption. One problem with this actually is that it's very sensitive to outliers. You can also look at other distributions. So robust estimate uses the absolute value instead of the squared errors, and so on. So in a way, you can think of this just heuristically as it's sort of a penalty function where we penalize the model the further it gets from the data. One fly in the ointment, the So one thing we're interested in is the measurements. Another one is the system state in the model. So the model might not reflect everything that's happening. So if you think about a model of an emergency room with patients getting admitted and discharged, here's the classic SD view. We have an admitting process, which depends on a constant plus maybe an effective weekends and other things like that. And then we have a discharge process, which is just patients divided by a time to treat them. That's great, but in the real world, you have other stuff going on. You have crowding effects that you may not have modeled, which might affect admissions and discharges. And you also have randomness, weather, just the Poisson noise of people showing up and finishing, different composition of problems. That means the state of the model could deviate from reality. And we can compensate for that by assuming that there's some unknown driving noise affecting the model, which is sort of an additional net flow on all the stocks. And in addition, there are some measurement errors in the data gathering process. And these things together mean that the model and the model's evolution might not reflect the structure precisely, and the data doesn't reflect the true state of the model precisely. So as we're simulating, if we're just doing conventional simulation, we start the model at a data point and let it evolve. We get to another data point, the model's now far from the actual state of the system. That's potentially a problem because the response of the model that we're asking the model to have now might be, it's operating in a different part of the state space. So it might be responding differently than it would if it were at where this data point is, particularly if the model's nonlinear. So we can fix that by using the Kalman filter to update the model state towards the data. So basically we come to this data point and say, wait a minute, the data says we're here. Let's update the model state towards the data. Question is, how far? If we think the model's reliable and the data is unreliable, then we might only move a little towards the data. If we think the model is unreliable because there's a lot of disturbances and unmodeled things going on, and the data is very reliable, then we'd move most of the way towards the data. So Kalman filtering is a sort of an add-on to the process so that we update the state of the model towards the data. And therefore, the model always reflects kind of the best combined understanding of what the data says and what the model says. And what the model says at a point is the accumulation of what the model said a priori, plus all of the data it's integrated up to that point. The next step you can take is going Bayesian. And this is sort of a funny thing. It sort of reminds me of the joke that the debates in academia are so bitter because the stakes are so low. This is sort of actually, it has the flavor of a big religious schism, but really the consequences for decision making, I think, are actually very natural from Bayesian inference. But a lot of people will tell you that it's a weird cult. I think it's just a tool like all our other tools. So don't take philosophical debates too seriously, although it's extremely interesting to ponder these questions, and just try to use the tool to get the most you can out of it for the process of making decisions with your model. And really, I think it's likely that you're already a Bayesian because system dynamics, in a sense, is fundamentally Bayesian. We use lots of prior information about the model structure and parameters sourced from the literature. We're rarely in kind of the frequentist mode of estimating everything in a model from the data and trying to pretend that we can get it purely from the data. And you probably also use model structures that are fundamentally Bayesian. The Kalman filter is Bayesian, and smoothing is Bayesian. So every time you have a perceived price that's a smooth of actual prices, that's adaptive expectations, which is basically Bayesian. And if you have a lot of data, it probably doesn't matter. The answer is probably the same either way because the data dominates. So what's different in this perspective? What we're after is a description of the distribution of the parameters, the plausible distribution of the parameters given the data and the model structure. That's the answer. Traditionally, we estimate that just from the likelihood of the data-driven likelihood. So the chance that the model could generate the observed data. So if you're going Bayesian, you just add a new term, which is the priors on parameters, expressing your belief about what is plausible a priori for those values. And you might regard that as a way to use information sources that comes from other scales of the problem or other similar problem domains or past modeling efforts. So there are lots of ways to choose these priors. I get into these a little bit more in the video, but I think most of the time we're interested in informative priors, but all of these things actually have some pitfalls. Here's an example. If you're building a model in which people respond to the price of some commodity or the copay on their healthcare, the price of their COVID test, you need some sort of price elasticity to characterize that. But if you look at literature estimates of price elasticity, they're all over the map and they're not even internally consistent. Some short-term price elasticity estimates are higher than long-term price elasticity estimates. And a lot of the short-term estimates are just fundamentally impossible because if you think of it as an oil price, for example, if the price were to go up by a factor of 5 like it has with the super low elasticities, the entire GDP of nations would be consumed on oil spending. So that's impossible. So you've got to be a little bit careful about how parameters sourced from literature or from what people tell you actually intersect with the model. And this is true of lots of things, and actually not just if you're expressing this as a prior, but even if you're just doing this intuitively. So prior is really just, you can think of it as a free data point in which we just look at the gap between estimated parameter and our assumed value or our prior on that value and our uncertain expression of the uncertainty in that value. So these just become additional terms in the payoff function in the model. So this is a view from our COVID model. So we've added a new view to the model. We have a view for structure, the SEIR chain. We have a view for data, and then we have a view for priors, which basically characterize how do the parameters fit with our prior assumptions from literature. So for example, you see R0 here, and there are early estimates that it was between, say, 1.5 and 4. So we essentially codified that as an expression here that said, we think it's 2.5 plus or minus 0.5. And these just become additional terms in the payoff function. The table here is what the list looks like. So the first 4 items here are data series on tests, hospitalization, deaths, and mobility with different distributions. And then the last terms are a bunch of priors. And actually, we had a lot more priors than we had time series data because there were lots of things for which we had some opinion going in. So what does that give you? It gives you confidence bounds, which you can think of as, in kind of the frequentist view, is the effect significantly different from zero? Or in the Bayesian view, what do we believe about the parameter after we've seen the data and integrated our priors? But practically, we're interested in this because we want to know what uncertainty implies for policy. So to do that, what we want to do is understand what does the likelihood surface look like from the model. So how does the model's fit to data vary with the combination of all the parameters, or maybe not just the fit to the data, but the fit to the data and our priors. And we can then estimate confidence bounds by essentially measuring how does the likelihood, which is the gray contours here, respond to changes in the parameters. And things are seldom nice ellipses. They're often weird, complicated shapes. So we're trying to, again, characterize the green piece here, our posterior understanding of the likelihood of different parameters given the data and our priors. And I'm going to skip a little here just for the interest of time. So how do we get that? One way is what's called Markov Chain Monte Carlo, which is basically just a process of unleashing a random walk on the likelihood surface. And it turns out with the right distributional assumptions, the random walk will spend most of its time in the most likely portions of the likelihood surface. So it'll generate a sample for you that reflects the underlying probability of parameters A and B. And it works even when the surface is not well behaved, in the sense that it will wander a complex surface. It doesn't have to be limited to an ellipse like traditional methods. You may still get computational problems if they're isolated, distinct surfaces. You start to need a strategy that has that's robust to that. Here's an example from our COVID model. So this is a scatter plot. The x-axis is the fatality rate, and the y-axis is two different growth parameters, one being the initial growth rate of infection, which we use to calibrate the transmission rate, and the other being historical effectiveness of isolation, meaning isolating people who test positive. And you can see the growth rate is very well determined by the data and the priors, but the isolation effectiveness is not. And you can also see that there's some correlation between these things. So high fatality rates imply low historic isolation effectiveness. And then you can take that output and plug it back into the model as a sample and simulate the ensemble of simulations using that sample to get a distribution of future possibilities for the evolution of the model. And then you can compare policies under that uncertainty. So here are.
Hey, Tom, there's a question at this point, if I could
Sure.
halt you for a second. Yeah. The question was, what type of Kalman filtering? Like, most of us probably don't know it very well. Are there different types the person wants to know?
I kind of glossed over that. So in Vensim, you have an extended nonlinear Kalman filter that essentially assumes the model can be linearized, and the Kalman filter is assuming that errors are Gaussian. The generalization of that is particle filtering, which Nate Osgood talks about. It's in the references. And you can relax some of those assumptions at some computational cost. The big problem with filtering in general is that you have to simulate thousands or millions of particles, or you have to assume things are Gaussian and simulate not just the variance of the model states, but also the covariance, which takes if your model has 10 states, you have 100 co-states measuring the variance matrix, and that's very expensive. So the conditions under which you can use it are kind of limited by that complexity. Didn't work, worked for individual states in our model, but we couldn't do all 50 states because that would have meant, 50 by 50 covariance matrix for every single state in the model. So it would have been 7,500 states squared, which was infeasible. The big challenge here, actually, I think, is not so much getting to this kind of description of policy. So here you can see policy outcomes, not just on the best guess for here number of deaths as a metric, but on the distribution of number of deaths. So you can see where not the tail risks vary, essentially. The big problem here, actually, I think, is visualization and communication of this results to decision makers who aren't used to thinking in this way. When we showed this to people, we had to spend a lot of time explaining what we were talking about here. And we've tried other visualization approaches and it didn't help. I think there's just an education process and you have to allow time for that. On the other hand, if you're making decisions without any appreciation of the uncertainty, then to some extent, you're shooting in the dark. So, bottom line, I think Jay was wrong. Fitting the model to data doesn't make it worse. You can't make the model worse by performing an additional test on it. It's also really hard to make a sensible model fit arbitrary data. Von Neumann had this famous quote that, if I have 4 parameters, I can make my model draw an elephant, and if I have 5 parameters, I can make it wiggle its trunk. It's just not true. If you have a model, if the model also has to be kind of dynamically sensible and nonlinear in appropriate ways and does, basically does stocks flows feedback right, it's very hard to get it to produce behaviors that are other than what is kind of fundamentally structurally determined. Also, I think if you can't reproduce history, you have some explaining to do, especially when you go out in the wild and confront decision makers who expect to fit to history. Even if their perspective is wrong and it's a weak test of the model validity, it's probably a hurdle that you have to pass. Otherwise, nobody's going to pay attention to you. So that makes data an important information source. It's not sufficient to assess the model, but it's a necessary step. And then finally, one of the reasons that that's true is that the intuitive characterization of system behavior or decision rules that you get from people involved in the system may simply be wrong. So when people tell you, yeah, we order more supplies or more beds based on X, Y, and Z, when you check that against the data, there's something missing. And that something may be extremely important in understanding the pathology of the system. But at the same time, Jay was right. You've got to start with a good model. If you don't have a good model that's sort of good in all the other ways that we try to enforce in classic SD, there's no point going through an expensive and time-consuming fitting exercise on a dumb model. And the model critically should reproduce all possible realizations of the data, not just the one you saw. And in particular, that means you have to be able to recreate things that are outside of the historical experience that you've seen in the data. If you're not robust in that space, then you can't make decisions outside of the past data. And if you can't make decisions out of the past data, then what are you doing? And Jay was also right in a sense that there is a mechanism for focus on data to make the model worse, which is you spend too much time on the data and not enough time on the model. So you do need to carefully balance your use of data against your use of all the other tools in the toolkit to make sure that not only have you built a good model that fits the data, but you've communicated it to people adequately and explored all the scenarios that are really of interest to them and brought them along so that their mental models have evolved, as well as getting an answer received from you and so forth. In short, there's a gigantic opportunity here if you're willing to take the time to learn the methods and balance the use of data against the use of the model. And I think maybe one implication here is we just need bigger teams so we can do all of these new things, but stay really sharp on the core things in system dynamics that are kind of in our genes about stocks, flows, feedback, nonlinearity, and building really good, robust models. So I hope this was helpful to you. I'm happy to stick around and answer questions. And again, I'll share this presentation, and there's some other interesting references in the literature that are a good jumping off point for thinking about these things.
Hey, wow, Tom, thank you so much. That was a lot. You told us it would be a lot. It was a lot. Many of us are going to have to go back and watch this once or twice or three times before all of it sinks in. But I think the cool thing is that it kind of tells us what's possible, even if it's not, we don't have the chops right now to do it. It helps us be realistic when we talk about what we are able to do with or without some of these fancy things. And it just, it's really
right. And I think the key is, 80-20 rule. Most of the benefit comes from kind of the early steps. Get the data into the model and start just looking at the comparisons and doing hand calibration. You get a lot of value out of that. Particularly you just learn which parameters actually matter. All the Bayesian and Markov Chain Monte Carlo and the fancy stuff, actually it's mechanically not that hard, although I think we have a lot to do to make it easier to use. All that, that's probably the other 20% of the benefit.
Well, let me just say, I'm going to leave the recording on for another minute or two if anybody has a burning question. Otherwise, we might turn it off and then have a more informal chat for those who want to stick around.
Well, I just wanted to say that I especially appreciated, Tom, your description of not only the model being iterative, but the data themselves. Because I find that to be true. And I think a lot of people are afraid of data because they think they need to get it all in there at the beginning. And that's not the case. You dive deeper into the data just like you dive deeper into the model itself.
Yeah, absolutely. And certainly that was true in the COVID experience. And in addition, what was a little unusual was that a lot of new data was revealed as we went along. There are other cases, for example, in, say, aircraft assembly, where we discovered kind of partway through the project that there was a key that couldn't be resolved with the existing information. And we had to go back into corporate systems to extract some data in a novel way to try and understand what's the average level of experience of workers on the assembly line. So two kinds of learning there, partly having that data, you could then answer the question about what's the role of experience in assembling aircraft. And partly, because it turned out to be important, that was something that they needed to be paying attention, that they weren't paying attention to because of the way their reporting systems worked. And I think there are a lot of cases where that is an important learning, is that, essentially the successful policy is to close some missing feedback loop, and that might involve data.
That reminds me of Donald Meadows' Dancing with Systems. That's what this is. It's a dance.
Right.
Any other burning questions?
Yeah, Tom, this is John. I'm not sure if I heard you right, but you made mention of the fact that when you do the MCMC and you get all the possible combinations of the parameter space and you use that for sensitivity analysis to run the model to get the possible, sensitivity or the variations of the results. Are you saying that, I'm not sure if I heard you right, that you're saying that you are able to simulate the future possibilities of the results based on that MCMC results? Is that an accurate statement?
Right. So it's using the model in a predictive sense. I think Jay's cautions about forecasting still apply, that just, if your mindset is, I'm going to forecast what's going to happen and then I'm going to react to that, that's usually not that effective, because the time scales over which you can forecast and over which you can react are different. But if your mindset is, I want to characterize the uncertainty in the future of the model, including the uncertainty in the response to things I might try, policies I might try, then what you want to know is, how does the future trajectory of the model respond to the policy change that I'm going to implement? And that may involve understanding the joint distribution of the parameters. So I had an example here. So you can do this kind of intuitively by saying, well, I think the fatality rate is between 0.7 and 1.4%, which would sort of characterize the x-axis of this orange blob. And I think the isolation effectiveness is between 30 and 70%. But what you can see here actually is that these two things are related. So just specifying the marginal distribution of those two things doesn't fully characterize your uncertainty about the problem. And there are lots of cases where that's true. So for example, if climate sensitivity is high, then ocean heat uptake must also be high, and vice versa. And so kind of your intuitive specification may miss features of the uncertainty, which in general probably makes the outcome look too uncertain. So the nice thing about Markov Chain Monte Carlo is it gives you the joint distribution of all the parameters. It tells you not just how plausible is the R0 or the growth rate or the generation time of infection. It tells you how all of those things combined produce the uncertainty that you're observing between the model and the data.
Thanks, Tom. There's a question in the chat from Maurice, and he says, what surprises about model parameters or structure emerged from the MCMC filtering stuff? And for example, at what point did you have high confidence about the proportion of asymptomatic, that kind of thing?
Oh, that's a good question. Actually, we've probably inadequately explored that just because we're under such intense time pressure. But actually, the sort of this correlation between isolation effectiveness and growth rates, things like that, there were some surprising features there. I guess I don't have a good example from COVID. I can think of another one from, I've mentioned I've been working recently on chronic wasting disease in deer. And we didn't do as much model data comparison as we would have liked to, just because we didn't have the budget or the time for it. We were in a kind of a pre-programmed series of public meetings. So we had to do a lot of things intuitively, essentially, that we would prefer to have done formally. But there were some interesting surprises that came out of that process. One was that, and actually this should have been obvious a priori, but we realized that it was important that the testing process for chronic wasting disease only captures maybe 2/3 of the positive deer. The other third are kind of the early asymptomatics. And that means that the true prevalence of disease is actually quite a bit higher than you would assume from the measurements that you're getting. And even though actually that should be obvious by just kind of looking at the performance of the tests, nobody's operating under that mental model. And we didn't discover that until we started doing some calibration and couldn't get the model to behave right. And we realized we were just comparing the wrong pair of time series. We were comparing true prevalence to tested prevalence. So we had to improve our modeling of the data generating process to get it to fit. And that, unfortunately, that's kind of an unhappy insight, because it means the problem's worse than you thought, and the disease is 100% fatal. So a deer who has, on day one of infection is inevitably going to die down the road, at least as far as we know. So we weren't happy when we found that out, but I think it was important to know.
I think I'm going to go ahead and turn the recorder off just so we don't have a ridiculously long video.